Imagine a multi-step digital workflow executing flawlessly for 20 consecutive steps, only to crash and forget every operation it just completed. This is the core architectural constraint of agentic AI workflows. Large language models are inherently stateless. By default, they treat every prompt as a starting point, requiring developers to inject all necessary context into every interaction. Amazon Bedrock AgentCore Memory provides the managed enterprise solution to this problem, delivering session isolation and persistent long-term knowledge retention without the infrastructure overhead. Early AI deployments often attempt to solve statelessness by caching raw chat logs in a Redis database and feeding them back to the model. That isn't memory. It simply fills the context window until the system degrades. Designing a functional enterprise agent requires explicitly separating the real-time conversational event log from the asynchronous pipelines that extract and consolidate long-term insights. The first layer of this architecture is the synchronous short-term memory system, which captures turn-by-turn interactions so the agent maintains immediate context within an active session. This architecture processes live interaction in the top lane and asynchronous background processing in the bottom. Every user input generates a create event JSON payload, isolated by session and actor IDs. Data then passes down, where extraction algorithms parse logs for durable facts. By decoupling state persistence from the live conversational loop, the architecture allows for continuous context gathering without introducing latency to the user's interface. To process that background data, AgentCore utilizes built-in strategies. Models specifically tuned for semantic and user preference extraction parse the raw event logs to pull out structured, actionable facts. Extracted data passes through a strict logic gate. Add memory identifies unknown facts, creating distinct records. Update memory handles highly specific new information, merging details while preserving timestamps. Finally, skip memory serves as a filter, rejecting redundant or temporary states and immediately discarding the data point. Applying these strict consolidation schemas prevents the agent's context window from filling with redundant or conflicting noise over time. This structural rigidity scales beyond basic user chatbots. It is required for long-running autonomous workflows, such as iterative code deployment or automated supply chain logistics. These workflows rely on episodic memory. Instead of isolated facts, this system captures sequential slices, mapping specific tool usage to overall task outcomes. The episodic pipeline structures events into a precise XML format: situation, intent, action, and assessment. The action tag logs the exact internal tools and arguments deployed. Next, the assessment tag evaluates the result, committing a success or failure state to the memory record. Over time, AgentCore runs an analytical metalayer across these stored XML episodes, known as reflections. Reflections synthesize data across dozens of stored episodes. They identify which specific tool combinations consistently yield positive outcomes and map out failure modes that the agent should avoid. By accessing these episodic reflections, agents can dynamically adapt their operational strategies based on past mistakes, providing a behavioral feedback loop. This reduces the reliance on constant model retraining. For highly specialized domains, enterprise architects can bypass Bedrock's built-in strategies by deploying self-managed extraction pipelines. This node graph illustrates a custom extraction layout. AgentCore pushes an event notification to an SNS topic, routing through an SQS queue to trigger extraction algorithms inside a Lambda function. You control delivery flow using message count, token volume, or timeout thresholds. To integrate memory into event-driven architectures, memory record streaming routes creation and deletion packets straight into a Kinesis data stream. Developers control payload density, choosing between metadata for simple alerts or full content text extraction for immediate downstream processing. To enforce multi-tenant isolation across these streams, all records adhere to a hierarchical namespace organization, locking data behind strategy, actor, and session IDs. By utilizing Kinesis, engineers transform long-term memory updates from a polling bottleneck to real-time triggers that initiate downstream tasks across the network. Across the industry, engineering teams frequently conflate an agent's memory with retrieval-augmented generation. They serve distinct purposes. This matrix visualizes the boundary. Stateful AgentCore long-term memory sits on the left, while stateless RAG operations sit on the right. Long-term memory tracks personal context, mapping ongoing user states. RAG supplies authoritative external domain knowledge too volatile to store in a session. These systems execute concurrently, without data overlap. Long-term memory tracks who the user is and what they have done, while RAG dictates what trusted external sources say. Integrating AgentCore's persistent state mapping with RAG ensures agents are both contextually aware of their specific user and grounded by authoritative, real-time data.